In last class, we have discussed the chapter solution up to Henry's law. So today we are going to discuss the applications of Henry's law. First one, packing of soda can. In soft drinks like soda, the carbon dioxide gas is dissolved in water, and to increase the amount of CO2 dissolved, the drink is bottled under high pressure. So the pressure decreases suddenly and the dissolved CO2 which escapes as what bubbles. So that is why we observe this sound while opening a soda bottle. Next one is deep sea diving. Here, the scuba divers work under very high pressure underwater. So, because of this pressure, nitrogen gas dissolved in their blood, and when the divers come up quickly, so the pressure decreases suddenly, and the dissolved nitrogen forms bubbles in blood. This causes a dangerous condition which called as bends. So, you should familiar with the word bends and or decompression sickness. To prevent this, the divers breathe a helium oxygen mixture which reduces the nitrogen solubility. Next one, high altitude climbing. At a high altitude, the atmospheric pressure is very low and oxygen solubility in blood decreases. Therefore, the climbers may experience weakness, difficulty in thinking, and shortness of breath. This condition is called anoxia. So, just go through the word anoxia. Next one, aquatic life in cold water. Cold water contains more dissolved oxygen than water. So according to Henry's law, what the law of lower temperature leads to higher gas solubility. So therefore, the fish and other aquatic organisms survive better in cold water. Next one, thermal pollution. Sometimes the thermal power plant releases hot water into rivers or lakes. So the hot water decreases the solubility of oxygen in water. As a result, the oxygen level decreases and the fish and aquatic organisms may die. Next one, we are going through vapor pressure of liquid solution. It is very important concept to understand the Rolle's law. So the vapor pressure, it is a pressure exerted by vapors above a liquid surface when a liquid and vapor are in equilibrium at a given temperature. So here this concept is very important to know what is Rolle's law. Here Rolle's law states that the partial vapor pressure which in a solution of each component in a solution which is directly proportional to what its mole fraction. So the partial vapor pressure of PA is equal to V naught P naught A chi A, PB is equal to P naught B chi B. So chi A is equal to mole fraction of A. Then we are going to discuss the graph here. So this graph shows partial vapor pressure of component in a solution. The x-axis which contain mole fraction of component A and B. Here it is 192, no issue. Then y-axis which shows the vapor pressure. There are 3 lines vapor pressure of A, that you can consider it as a 1, no issue. Vapor pressure of B, it considered as 2, P2. The total vapor pressure. So as the mole fraction of component A increases, its vapor pressure also increases linearly. So the vapor pressure of B decreases because its mole fraction decreases. Then we know that what is P total, sum of both partial pressure. So P total is equal to P1 plus P2. That's why we get a straight line for total pressure. Then Rolle's law in combination with Dalton's law of partial pressure. We know that according to Dalton's law, what the total pressure equal to the sum of partial pressure of gases. So P total is equal to PA PB according to Dalton's law, right? Dalton's law. So and we know that PA is equal to what? PA is equal to chi A P naught A and PB is equal to what? Chi B P naught B. So substitute here the PA PB as chi A P naught A and chi B P naught B. Then we get the equation that P total is equal to chi A P naught A plus chi B P naught B. We know that chi A plus chi B equal to 1 for a binary solution. Then we substituting, we get P total as P naught A plus P naught B minus P naught A into chi B. How it comes? Actually, the 1 minus chi B we substituted here and both chi B is common for here. That's why we put chi B as outside. Then we got P total is equal to P naught A plus P naught B minus P naught A into chi B. Then we are going to discuss the Henry's law. Also at a special case of Henry's law. The both equation is such differ by the constant. That's why when therefore a Rolle's law become a special case of Henry's law, it is only proportionality constant case differs the P naught A. Then we are going to discuss the classification of binary solution. You are familiar with what is binary solution. So there are two types of binary solution, ideal and non-ideal solution. The ideal solution, it is the solution that obeys the Rolle's law at all concentration and temperature. So the characteristics, intermolecular forces between AA, and AB are similar. There is no heat change during mixing and volume does not change during mixing. So the example, benzene plus toluene, hexane plus heptane. Then graphical representation for ideal solution. So here there are axes here, two axes, one is x-axis and another is y-axis. X-axis showing the mole fraction and y-axis showing the vapor pressure. So in an ideal solution, the interaction between AA, and AB molecules are almost the same. Therefore, the solution obeys the Rolle's law. So here in the graph, the characteristic is visible that the straight line relationship. So there is no deviation from what the Rolle's law. So total pressure line is very smooth. That's why the graph, that's the thing the graph depicts. Then non-ideal solution. The solution which do not obey the Rolle's law. This happens when solute-solvent interactions are different from solvent-solvent interaction. There are two types of deviations. One is positive deviation from Rolle's law. In positive deviation, vapor pressure of solution which is greater than the vapor pressure they expected. Then the weak reason it becomes because the weak attraction between solute and solvent molecules. For example, acetone and carbon disulfide. So look into the graph. There are two axes, x-axis and y-axis. X-axis which given the mole fraction, y-axis which gives the vapor pressure. So the curve lies above the Rolle's line. So here we can say that in positive deviation, vapor pressure of solution is higher than we expected. So for example, what acetone, carbon disulfide and ethanol plus cyclohexane. Then cause of positive deviation we have discussed. Then negative deviation from Rolle's law. In negative deviation, the vapor pressure of solution which is less than the expected. So the reason which is what? The strong attraction between solute and solvent molecules. Example, you have to go through it. The example is that what? The chloroform and acetone here, enthalpy of mixing and an enthalpy of volume mixing which are negative. Then we are going through the what? The graph. In this graph, the curve lies below the Rolle's law line. So here the vapor pressure is lower than expected. So the solute solvent attraction is stronger and molecules cannot escape easily. So the lower vapor pressure here. Example what? Chloroform plus acetone and nitric acid plus water. Then azeotrope. Some mixture boil at a constant temperature without change in their composition. So there is no change in the composition. Such mixtures are called azeotropes. Azeotropes are two types. One is minimum boiling azeotrope and maximum boiling azeotrope. Minimum boiling azeotrope which shows the positive deviation from Rolle's law. Example what? Ethanol plus water mixture. Maximum boiling azeotrope which shows the negative deviation. Minimum boiling azeotrope which shows positive deviation. So here example HCl plus water mixture. Then we are going to discuss the colligative property. Colligative properties which are the property that depends only on the number of solute particles and not on their nature. So there are important colligative properties. These important colligative properties are relative lowering of vapor pressure, elevation of boiling point, depression of freezing point, osmotic pressure. These four colligative properties we will discuss in next class. And thank you for listening. Just go through the topics and study well. Thank you.